Okay, good morning, everybody. Welcome to this webinar from Flanders Make on managing complexity in product design. Before we start with the webinar, I would like to give you some practical information. First of all, there will be a possibility to ask questions, so there will be a question and answer chat. So please feel free to ask your question during the presentation on the chat. And we will try to answer as many as we can during this webinar, but please also indicate your name and surname. So if we are not able to answer all the questions, we can come back to you after the webinar itself. So I will start with a brief introduction about the topic that we are gonna discuss today. That's how to efficiently manage complexity in product design. I would like first to start to position this topic on the Industry 4.0 and the driving market force, which are three main driving market forces, which are smart interconnected products and production system, customized product, but at the cost of mass production, and sustainable human-centered production. And of course, always taking into account energy efficiency, cost efficiency, and recyclability. So if we see these trends growing in this new era, Industry 4.0, what are the implications for the design process? I can summarize this in one word: complexity. And why complexity? For many different reasons. First of all, the products are becoming are not anymore only mechanical products, but often are mechatronics. So we have different disciplines which are involved, different technologies, but also the products need to make more functions. You have many more design parameters where you can choose from. And also when we think at adaptable products, we have many more validation and verification scenarios we need to take into account. Again, if we look at mass customization, this means also that we need many more variants of such products. And finally, is also the criteria that we have to optimize our product are becoming larger and larger. It's not anymore only about performance or only about cost. It's also about, for instance, easy of assembly, easy of recyclability, and so on. So these increase the complexity. That on the other hand, there are many studies that show that when the product become more and more complex, the design efficiency decreases. But this is of course a problem, because if we want to have a smaller product series, we need to be more efficient in our design in order to stay competitive. And at the same time, as indicated, for instance, in the System Engineering Vision 2025 from Heurisko, there is an evolution in technologies which is quicker and quicker, and the customer expect to have the last technologies in the product. This means that the times to market pressure become even larger than before. So we have three aspects, being complexity, need to increase in efficiency, and shorter time to market, which are in contradiction, let's say, with each other, and which creates many challenges. That's the reason why within Flanders Make, in the cluster of design and optimization, we focus on developing methods and supporting tools to support the designer, to support the company in managing such complexity in a time and cost efficient way by making the right choices. Just briefly, two things I would like to mention is where do we focus to increase efficiency is to focus on the early design phases, where most of the costs, the decisions that are taken in these phases determine the larger part of the cost of a product. And also because if you have iteration design changes later in your design process, of course, these are much more costly. And two aspects we believe will help in managing this complexity. In one end is a model-based design approach, but also thanks actually to the Industry 4.0 era. So we have many more data coming and digital twins of products that are in operation, and this data and this information can be fed back to the design of a new product in order to make the right choices. So this was a brief introduction, and I come back to my slides on complexity and the different aspects. So we have today 3 presentations. We deal with one of these aspects and how we can help in managing such complexity. The first presentation will be given by my colleague Philippe Eyckens from FlandersMake and from Marco Panzeri from Noesis, which deal with evaluation, generation and evaluation of concepts, evaluating for many different criteria. The second presentation, it also deals with different criteria because it deals with a multi-objective optimization and the developments done there, and where also we have to take into account many design parameters. This presentation will be given by Sander Dedoncker from FlandersMake. And the last presentation is about disciplines, bringing together control engineer and embedded software engineer in order to improve the design process and to reduce late iterations. So I would like now to give the words to Philippe for the first presentation. Thank you.
Yes, thank you, Paula, for this introduction. I'm very happy that I can present together with Marco of Noesis this collaborative, this joint work on the design concepting and optimization. So here's the outline of our talk today. So I will first briefly introduce the design challenge at hand. And then outline the followed approach, so a very generic approach. So I'll explain what is the methodology and also how it is implemented. This is done in 2 coupled software pieces. So the first half of this coupled software is I will introduce this. This deals with the stage of design concepting. And here we will go from initial 1,800 design concepts and narrow it down to 5. And then Marco will take over to tell more about the second stage of design optimization and going further to a single detailed optimized design in the end. So the design challenge we have is a commodity product, the passenger outer panel of a vehicle. So it also deals with the reinforcement structure as main functionality. And the objective here is cost minimization of the production process. Of course, there's many functional and other requirements that this product needs to fulfill. So the idea, the challenge is not to make an incremental design improvement from an existing product, but we will start from scratch. We will want to think out of the box, and in this way we can enable more innovative solutions or maybe even disruptive. So the challenge really is to do ab initio redesign of this product. And then a very first important preliminary step is to look at the constraints and formalize, and that means quantifying as many of these requirements. So for example, so in this table there's a lot of constraints quantified, but we can define some mechanical load cases like impact load and so on, and then put constraints on the stiffness of the structure, on the strength and fatigue life, for instance. So then the methodology, an overall overview here. In the design concepting phase, here we will start not by drawing by hand, so to say, but use computer algorithms to generate some candidate reinforcement designs. And so we can easily reach 1,800 candidate designs. And of course, then how to make sense of it, we need to quantify the attributes that are relevant. And we have ranking algorithms and other algorithms, so we can have methods to very easily select the best concepts. And so we select a handful of concepts to go to the second stage of optimization. Here we explore the design space more in detail, and we will finally go to optimization with constraints. The implementation, so at the first stage, this work is done with the concept evaluation workbench developed at Flanders Make. So this is a FreeCAD based software. So FreeCAD is open source Python CAD program, also with simulation capabilities. So we have added functionalities here. So you see here some extra buttons in the GUI, and they can deliver the workflow sketched here. So we have functionality for automatically generate concepts. Can also be done manually, of course, by drawing a cut. But we won't go into this aspect today. From the set of formalized CAD concepts, we unleash a number of attribute models ranging from stiffness to manufacturability. This gives us a performance metric. And upon this, we can filter and apply ranking algorithms finally to reveal the most promising concepts. And then we go to the second stage, and Marco will now explain the tool used here.
Yes. Thank you, Philip. Indeed, this slide describes from a general point of view how the second design optimization stage has been implemented. The rationale is that the identified concepts during the conceptual design stage are used in the second detailed design stage to investigate how parametric variations on the variable that are typically kept fixed during the conceptual design can further be optimized through the usage of design exploration and optimization algorithms in order to further improve the performance of the corresponding concept. In this study, these parametric analyses have been performed with the aid of the Optimus platform, that is a commercial platform produced by Noesis solutions that encapsulate the following key capabilities. The first one is process integration and automation that provides a graphical environment to define simulation workflows, as the one that is shown here in the slide. For example, this workflow is the one that has been used to automate the generation of parametric concept variants, drive the execution of the attribute calculation that is always performed under the hood by the conceptual workbench, and retrieve the results that are generated by these Flanders Make tools. The Optimus provides also a rich library of design space exploration, optimization, surrogate modeling algorithms to run studies on top of this workflow environment, together with post-processing capabilities to inspect the results that are produced through the simulation workflow.
Okay, so let's now go into the details. And so starting from the design concepting, to automatically generate these beam reinforcement structures, we put in place some algorithms. So by applying, we view this as a constraints problem. So applying linear programming routines in consecutive steps, we can generate the structures. First step is a topological step. So here, the beam connectivity is in fact ensured under a number of constraints. To give one example, a constraint can be that we impose that the structure connects some hinge locations over on this side of the door to the opposite side where the lock is situated. So this space needs to be spanned. So this is something that is typically covered in this stage. So then the next stage we put the geometry. So the joints of the beam structure are allocated some positions from a grid. And again, here we have constraints like this broad, like this window area that we don't want any beam structure to pass. So this is a geometric constraint added at this stage. And by doing this, we can generate a large set of topologies very readily. And we go then to the next stage, attribute evaluation. So just going very briefly over the attribute models that are included and are relevant here. So these the relevant attribute models for today's topic are highlighted here in yellow. Firstly, it's the cost model. So here we have actually several options ranging from a formula-based cost model taking into account material cost, production cost of primary and secondary processes, but also a link to the embedded part cost estimator module of the CES material selector. So this is also fully automatic and in place. We have model for the stiffness of structure, the strength and fatigue limit also. Here we link the Conceval workbench to the finite element routines for mechanical analysis. Also for NVH properties, what we will show today is work on the eigenfrequency. Here the modal analysis has also been linked. The manufacturability is this is a comparative model, so where the main parameters of the production are taken into account, like number of components, the weight of the heaviest component, and so on, process diversity, items like this. And we also, of course, we consider the mass. And beyond this, there are other two models more customized to different problems that can also be exploited, of course. So then if we go into if we have really run these models, we finally get this performance metric, and you see here just a very small part of that, because of course this is a large set of data. So how to make sense of this? So first we can apply filters, so concepts that do not meet minimal requirements on attributes we can easily throw away. And what's left then, we can apply several ranking algorithms. So each ranking algorithm will finally give a score to each concept by somehow comparing the different relevant attributes. And in this way, we have selected 5 highly promising candidates. So I will shortly show them to you now. So we have a 3-beam concept here. And as you can see here by the colors, this has very favorable cost, mass, and manufacturability properties, but it is less beneficial for some structural properties. So the red means still a property that still meets minimal requirements, but is relatively less favorable. The second concept, outer frame concept, is other way around. So it has good functional behavior, but it weighs a bit more and costs a bit more. A broad window concept is the third. This one has especially good property on the resonance resistance, as you can see at the by the large first eigenfrequency of this concept. An S-shaped concept here, also good for some structural properties. And lastly, a truss frame concept, also balancing in some other way all the different attributes. So an important note to make at this stage is that the that we are comparing really the design layouts so far. So we have just used a single material, a single cross section for all these beams of the structure. Only now we will make more detailed design, and this is what Marco will discuss next now in the next stage.
Yes, in this slide and in the next one, we will dive into the details of the detailed design stage. We have set up a strategy that is implemented in 2 steps. The first one entails the design space exploration study that is run to gain insights on the variability of the key attributes of interest, and also to compare the performances of the 5 candidate concepts that Philippe has introduced before. In our study, we considered variability in the material of the beams. As candidate materials, we will consider steel, aluminum alloys, polymers, and PMMA. And besides these, we also consider variability for the cross-section geometrical parameters of each beam. The objective of this design space exploration study is also to narrow down the selection of concept. In our study, we have selected out of these 5 concepts 2 most promising concepts that are then adopted during the second step. The second step entails the real design optimizations, where the ultimate goal is to identify what is the optimal or best configuration for these 2 selected concepts. The next slide describes the results that have been obtained during the first step, so the design space exploration analysis, which in total entailed 2,500 functional evaluations, so numerical experiments. The scatter bubble plot that we see here shows how the first again frequency and the stiffness of the concept variants that have been generated vary among the generated variants. Here the color scale is associated with the type of concept, while the size of the bubble represents the cost. The plot demonstrates 2 different aspects. First of all, for each single concept, there is a huge variability in terms of performances, especially if we compare these clouds of points against the nominal points that have been obtained by considering the fixed parameter values. However, among this huge variability, it is also possible to identify that for each concept has its own inherent advantages and limitations in terms of NVH performance, for example, or structural performance, suggesting that there is the possibility to further select among these 5 concepts the ones that are most promising according to the functional requirements that are defined for this case study. And this is the aspect that is investigated and presented in this slide, which visualizes all the generated concept variants on this parallel coordinate plot, where all the attributes of interest are displayed on the several vertical axes. If we apply a filter on all these generated variants, we can quickly see that indeed only 2 out of the 5 concepts can meet the constraints that we are imposing on manufacturability, first again frequency, and stiffness. And this is the rationale that led us to select these 2 concepts, the outer frame concept together with the broad window concept, for the parametric optimization studies. So for each of these 2 concepts, an optimization strategy has been run targeting the minimization of cost. The design variables that we are adopting for this stage are the same as the one used during the DOE. So material beams and cross-section parameters, and the constraints that have been applied are related to NVH performance, stiffness, and manufacturability index. In terms of optimization algorithm, we adopt a hybrid strategy that couples genetic algorithms together with surrogate model to find the optimum in an efficient way, entailing the least possible number of function evaluation. The optimal configuration are the ones that are displayed here, showing that indeed the optimization can lead to huge reductions in terms of cost and weight for both concepts. But as you can see, the achieved cost and weight reduction for both the selected concepts are relatively close to each other. And from this, again, parallel coordinate plot, is also clear that there is one of the two concepts, the broad window concept, that is associated with a better NVH performance. And this was the rationale, the logic that we used to select as optimal one, the broad window concept. And that's basically the final selection of the case study of the concept, optimal concept, so to say.
Okay, so and then we can come to the conclusions now. So as Marco just showed, we have demonstrated here in this case a very good reduction of the cost through lightweighting mainly. Also, I want to emphasize that by starting with about 2,000 different architectures for the reinforcement structure, we also can have a great confidence that finally we can reach a global optimum. And well, at the same time, this workflow leads to very novel, innovative solutions as illustrated by the broad window concept. As an outlook, so we have already started to apply the same methodology to the DAF truck cabin door you can see here of the XF series. So so we also will apply the same methodology, the same collaboration. So we're very excited about this, and this will be done in the framework of the Light Vehicle 2025 projects that's supported by the Interreg program of the EU region Meuse-Rhine. And with that, I'd like to conclude our contribution and give the word back to you, Paula.
Thank you, thank you, Philippe. Thank you, Marco, for the very interesting and clear presentation. I would like now to give the word to our second speaker, Sander. Before I do that, I will also like to remind you that you are more than welcome to post questions to ask for clarification during the presentation. Thank you. Now I give the word to Sander for the next presentation.
Okay, thank you, Paula. So good morning, everybody. My name is Sander Dedoncker. I am a PhD researcher at KU Leuven. So I'll be offering a bit of an academic perspective today. And the theme of my talk is very similar to the previous one. So it's also about how to bring optimization closer to engineering design. But I will be focusing more directly on Pareto-front analysis, that is to say, multi-objective design. And the application I will investigate is mechatronic systems design. So content-wise, I will start with a brief introduction to set the scene and explain the main challenges. Then we will investigate what methodology we will be using to solve the optimization problem. And I conclude with an application, a case study in mechatronics design. So why is the mechatronics design problem interesting? Well, it's certainly very relevant. It appears in many different forms, and it's also quite a challenge. There are at least three main groups of challenges that occur. First of all, mechatronics is a multi-physical system, so there's at least the mechanical and the electrical part, but sometimes it gets even more complex than that. And as a result of this, you also end up with something that I call a multi-model, which basically means that every physical subsystem may be simulated with its own dedicated software environment, and all these things need to be coupled somehow in the end. And of course, as with any design problem, mechatronic systems design is a multi-objective problem. So there are different objectives that need to be balanced against each other. So the question is, how do we support the designer And one possible answer to this question is to offer automated tools for optimization. In this case, that would be simulation-based and multi-objective optimization. Taking a closer look at the optimization problem itself, first of all, we have the black box or simulation-based aspect of it. So suppose you're creating a model of a mechatronic system, and you could have a Simulink type model for the control flow, a specialized gear contact code, or a more general purpose finite element solver. And all of these things are coupled somehow in your mechatronic system model. So in the end, you have a set of design variables that are mapped somehow via an objective function to a performance output. So setting this up is not that difficult. The real problem is that from a mathematical point of view, the function you are creating is quite tricky to optimize. So you can imagine that underlying the simulation is an idealized function that may be smooth, but because you're having iterative solution procedures, you introduce numerical noise, which means many localized minima, and of course also difficulties with applying finite differences. And of course, when you're having complex software environments, you introduce the possibility of errors or bugs. So the optimization method also needs to be robust against these things. So those are the fundamental challenges. You don't have derivatives, you may have hidden constraints, there may be numerical noise, and of course the system may also be expensive to evaluate. On the other hand, we have the multi-objective aspect. And the main question here is, how do we define optimality when there are multiple objectives involved? And it all starts, of course, with a system to rank different designs in this multi-dimensional objective space. So let's say we have two objectives here, and by convention, we're always trying to minimize things. So we are comparing now, let's say, 4 designs. And if we look at A versus B, we see that A improves both objectives with respect to B. So we can say that A is objectively better, A dominates B. And similarly, C dominates A. But if we're trying to compare A and D, we find that they represent different trade-offs between the objective functions, so they are equivalent in some sense. And if we take this concept to the entire reachable performance set, so that is all possible designs, and we look at the lower left edge, we find the Pareto-front, which is of course the solution to the optimization problem. It is the set of all non-dominated designs. And all that remains, of course, is to approximate this thing numerically, where the main challenges are to monitor and improve the approximation quality, both in terms of closeness to the front and diversity of designs. And there's also an aspect of visualization that can be tricky, but which I won't be focusing on in this presentation. So how may we approach solving the multi-objective and black box optimization problem? Well, there are different approaches. One of them is a list-based strategy. So what you do is you provide an algorithm with an initial list of points, and the algorithm will then automatically refine this list iteratively. So what it does is it selects an iterate from the list in every iteration, and then generates some new designs that surround this iterate, which then map to the objective space in some way. And hopefully you find some better designs that you can then use to update the list. And going through this cycle several times over, you end up with a final list that is hopefully a good approximation to the Pareto-front. One question that remains is, how do we select these new samples? And that takes us to the optimizer we're using here, which is direct multi-search, DMS, which is basically the multi-objective generalization of the common pattern search approach. So what it does is it generates new candidate designs by looking along different directions from the current iterate. And of course, it keeps the non-dominated points in the list. So as an example, let's say we have a two-dimensional design space, two-dimensional objective space, and these two are linked via the performance map. So we have a current iterate, the blue dot. And what DMS will do is it looks along different directions, let's say up, down, left, and right, to see if there's any changes in the design. So these points are mapped to the objective space in some way via the performance map. And we see that some of these points end up in the dominating region with respect to the current design. Some of these points are Pareto equivalent, and some will be worse. But the point is that by applying this procedure, you both refine the existing designs and generate new ones. So that's the basics of direct multi-search. It's effectively a state-of-the-art method, and it can achieve quite good spreads. It's also rather robust, but its main problem is that it's not adaptive because the search directions are fixed, so they don't take into account previous function evaluations. And that takes us to the research that we've been doing in our group, which has been aimed at accelerating DMS by adaptively choosing the search directions. So the idea is that by a smart choice of both the geometry and the orientation of the pattern, we can achieve better improvements to the design by using fewer function evaluations. For instance, you could apply a geometry and an orientation that looks like this, and you will see that the designs you find are better than the ones with standard DMS. So without going into further technical details, the principle we use is based on the steepest descent approach, which is borrowed from single objective optimization. And basically the directions that we're using here are optimal for a linear model of the objective function. That allows you to find better decreases to the function. All right, so that concludes the methodology section. So now I have a case study I would like to present. So I took inspiration from a classical design problem, quarter car suspension design, but I tried to make it a little bit more interesting than the classical linear model. So that's why I start from a 4-bar mechanism, which could represent a double wishbone configuration of a suspension. And between two opposing nodes of the mechanism, we have our suspension elements, which consist of a linear spring, a nonlinear damper, and a force transducer that is PI controlled. And so the body is attached on one end of the mechanism, the wheel is attached on the other. So with this model, I have in the end 11 design variables, so an 11-dimensional design space, which ranges over geometry and suspension parameters. So what we're trying to optimize here is, well, we're trying to simultaneously optimize two things. So it's a bi-objective problem, and I will be trying to trade off handling versus comfort. And in the next slide, I will explain what I mean by these things. But basically what we do in order to run the model is we apply a step excitation on the wheel and then run a dynamic simulation to see what the body end response is. In terms of constraints, we have, of course, bounds on the design variables, and there are constraints hidden in the system model, that is the physics. So yeah, what do I mean by handling and comfort in this case? To illustrate it, I have here two designs with different emphases. So on the left-hand side, we have a design that is supposedly good in terms of handling. So what I say is handling is that the suspension settles quickly after a road disturbance, so you have quick and responsive behavior. So I'll now run an animation, and you'll see that there's a step input at the wheel end, and the car body responds very quickly and very closely to the wheel input. On the other hand, we have comfort, which is mainly an issue of shock and vibration isolation. So if I apply the same input on the wheel end, a comfortable design will be much smoother on the body end. Right, so to implement my model, I just went to Simulink, which is very simple to do. It's basically like playing with virtual Lego blocks, of course. So it's appropriate for early conceptual design. But the drawback of using Simulink is that it's very difficult to analyze, of course, and all of the problems that you have with black box optimization or simulation-based optimization, they also occur for this model. So you have numerical noise, you have potential errors, etc., etc. And also the simulation time is quite significant. So running the model on my system takes about 30 seconds, which is already something to consider when you have a limited time budget. So basically the optimization method that we're using needs to be both robust and efficient. So in terms of results, I will now plot the Pareto-front that I obtain after 1,000 calls to the black box using 3 different solvers. So on the Pareto-front, we will show handling versus comfort. And as always, we're trying to look for designs that are closer to the left and to the bottom of the slide. So first of all, you could look at a genetic algorithm. which is the standard approach to solve these kinds of problems. And it achieves a Pareto-front that looks like this. If we refine our approach and use the state-of-the-art DMS method, then we already find a significant improvement of the Pareto-front. So a new region is explored here. And DMS also finds better designs in this upper left region over here. But we can do even better. If we apply the adaptive DMS method that we've been developing in our group, you obtain a Pareto-front in this case that is also very dense on most of the front itself. But the method also finds an outlier that is not discovered by other methods. So DMS, or the adaptive DMS version in this case, performs significantly better. And yet, once you have your Pareto-front, you, as a designer, you can do whatever you want with it. So, for instance, you could use it to define different product families or to identify trends that exist in the design space. Basically, it's just a way of informing the designer as good as you can. So, for instance, in the quarter car suspension design, you can see that there's a trade-off between handling and comfort. That mainly comes down to trade-off between a stiff and a soft suspension, which is, of course, not very surprising in this case. But in more realistic design problems, you may find more interesting conclusions as well. So yeah, that concludes my presentation. So as said, we need a combination of black box and multi-objective optimization techniques to design dynamic systems or mechatronic systems. And we can do the Pareto-front analysis in low to moderate design dimensions and objective dimensions. If we use the direct multi-search method, this already works, but if we apply our fast adaptive methods, we can do even better, or we can do this more efficiently, let's say. And yeah, so in practice, what can we do is we have MATLAB implementations of both these DMS methods, which are supposedly very easy to use. They basically borrow the syntax of standard MATLAB optimizers, and they don't require much advanced or expert input. And also because they are a black box optimizer, they are very versatile in terms of tool chain. So anything that interfaces to MATLAB can be used to construct your model. For instance, we've tried examples that interface with NX or interface with console. Basically anything goes, which is basically the main strength of this method. And also it generates very diverse Pareto optimal designs, so you can inform the designer as well as possible. And it's an optimization method, so that means it's not restricted to design optimization, but it can also be used for other problems, for instance, model identification. So that's all I wanted to say. I will be here for the Q&A if you have any questions, or you can contact me or my colleague via email, and then now I hand the word back to Paula. Thank you very much.
Thank you, Sander, for the presentation. Very clear, very interesting. Again, I would like to remind the participant that we have a Q&A chat. So there has been, in the meantime, a question. So you can see, if you click on the Q&A chat, you can see the question and the answer as well. And so please feel free to ask any clarification of question you have. Then we can go to the last presentation. So we step away from the mechanical, let's say, part of the design, and we go more toward the control and embedded software design. And Ken will present the EPSim tool developed at the University of Antwerp. Ken, the floor is yours.
Thank you, Paula. So, as stated by Paula, in the next 10 to 15 minutes, I'm going to talk about EPSim, which is a simulator that enables you to co-simulate your control algorithms and your embedded platform in one and the same environment, and in early stages of the design process as well. And as such, we state that it enables you to do virtual hardware-in-the-loop simulation. Let me start by a small example, a scheduling example. So consider that you have an embedded platform shown here on the right, and that the embedded platform runs in a real-time orbiting system with a fixed priority primitive scheduler. and 3 tasks needs to be scheduled. The first task has a priority of 4, a period of 10 milliseconds, and execution time of 4 microseconds. The second task has a priority of 5, same period, and execution time of 5 microseconds. And the third task has a priority of 6, same period again of 10 milliseconds, and execution time of 22 microseconds. My question is, how is it scheduled? Since we're in a live meeting, I'm going to provide you the answer, which is the following. The first task will be scheduled immediately, so its response time will be the same as its execution time, which is 4 microseconds. The second task has to wait a little bit before the first task has completed, so its response time will be 9 microseconds, which is a sum of 4 microseconds from the first task and 5 microseconds of execution time of the second task. And the third task, well, you can figure it out by yourself. Its response time will be 31 microseconds because it has to wait for the first and the second task. Why do I show you this example? To clearly state the difference between execution time and response time. So typically, if you're designing a control algorithm of a mechatronic system, you will start in Simulink by modeling your control algorithm. You will then generate code out of that. And of course, you want to know how much time your target platform will need to execute that code. So you will deploy it bare metal on your target platform, and you will measure its execution time. Of course, if your mechatronic system consists of multiple control algorithms, shown over here, so we have n control algorithms, and that they need to be run or scheduled on the same processor, then, as stated before, you will cluster them in several tasks that needs to be scheduled by your operating system, and as such, your response times might be higher than your execution time, as shown in the example. And why are these response times relevant? Well, I show you this because often, if you're designing your control algorithm, for example, in Simulink, you're ignoring those response times in early stages of the design process. So if you have designed your control algorithm in Simulink and you push the simulate button, then your system will be solved, but in the same time, so at the same one and the same time stamp, your inputs will be sampled, your subsystem will be solved, and your outputs will be set in Simulink. But in reality, if your control algorithm runs on your embedded platform, that will not be the case, because between sampling your inputs and solving your system and setting your outputs, there will be some time, which is called response time. And this is typically not included when you're designing your control algorithms in Simulink. And EPSim tries to solve that problem by including those response time when you're designing your control algorithms. So let me tell you a bit more about the what, the why, and the how of EPSim. So to clearly state why we developed EPSim, I'll show you this slide. So if you, again, I'm repeating myself, but to clearly state that if you design your control algorithm in Simulink, you connect that typically to a plant model, perhaps you have a feedback loop, and you simulate your behavior in Simulink, and everything looks okay. But if you deploy that and you include your distributed platform, your software components of your control application will probably be deployed in a distributed way. You have some time delays due to the network, and of course, your behavior might differ from your simulated behavior in Simulink. And this is what EPSim tries to avoid by including this embedded platform in the design, so that you can evaluate the deployed behavior in early stages of the design process. And how do we do that? Well, EPSim, depicted here as a cloud in the middle of the slide, requires some input to do that. The first input is an architectural overview of the platform, so that includes the processors that are used in your target platform, some kind of network that is included in your platform. So it needs that as an input. It also needs your software application or your control algorithm as an input. It needs some timing information of those components that will be executed by your platform. And as an output, EPSim allows you to connect those software components to your, or allocate those software components to your embedded platform, and to show you the real deployed behavior in the simulated environment. But what is EPSim exactly? So that cloud in my previous slide represents a library of different models that EPSim provides to you. So EPSim provides you models of tasks, interrupts, processors, schedulers like a fixed priority preemptive scheduler, but also communication models, communication medium models like SPI buses, CAN buses, USART models. That's all included in EPSim, and also some input-output peripherals like an EDC and a DEC are included in EPSim. Those libraries you can use to model your embedded platform. What can you do with EPSim? Well, as already stated, you can evaluate your deployed behavior at early stages of the design process. You can explore different deployment strategies. So you can evaluate if you have a contra application with software component 1 and software component 2. You can evaluate what the response times are in different scenarios. Let's say software component 1 has in first case a priority of 1 and software component 2 with a priority of 2. You can evaluate this behavior with the behavior where you switched the priorities. And you can also evaluate the impact of timing delays, which might be introduced by your network, as stated in this slide. So what is in it for the industry? So in the CSE Eyckens project, which is currently running, we are at this moment evaluating EPSim with some of the companies that are involved in the project, and one of those companies is Vanherpen. And Vanherpen, they are designing and selling loom weaving machines, as shown over here on the left. And during the loom cycle, which is 360 degrees, in a certain point in time, the weft yaw needs to be cut by scissors. And in the Vanherpen case, that needs to be at exactly 20 degrees in the loom cycle. Of course, the scissors that are used to cut that weft yarn are activated by some electronics. And the electronics consists of an embedded platform, which is a distributed embedded platform with 2 ECUs connected by a CAN bus. And the scissors itself is actuated by a black box device, which is connected to the embedded platform by a second CAN bus. The black box device, of course, actuates the scissors at a certain point in time in the loom cycle. Of course, the electronics introduces some delays. So the first category of delays are the sensor delays. So it needs some time for the sensor to get to your algorithm. Algorithm calculates when exactly the scissors needs to be activated, and of course there's also the delay of the actuation, which includes the second CAN bus and of course the black box device. So what can EPSim do in this case study? So EPSim will try to figure out at which point in time the send command needs to be, well, the cut command needs to be sent. EPSim tries to determine the exact point in time in the loom cycle at which the cut command needs to be sent. So how do we do this? Well, the electronics are modeled using EPSim. So EPSim provides some libraries to do so. So the platforms are modeled in this way. So we have a model of their ECUs, which includes the certain scheduler, also the tasks that are running on the platforms are modeled. The field buses or communication buses are also modeled. Those are typical. In this case, they are both CAN buses, and the black box device is also modeled using a separate model. So the entire electronics is modeled as such. So all of them can be connected to each other. and the center delays and the actuation delays are then included in your model. And as such, EPSim determines or can determine that the send command, the cut command needs to be sent at 5 degrees in the loom cycle. So if the weft yarn needs to be cut at 20 degrees, then EPSim tells you that the command needs to be sent at 5 degrees. And EPSim is also able to include the stochastic effects of your embedded platform, as shown over here with those Gaussian distributions in the graph. So what are the key takeaways of this presentation? What do you need to remember? You need to remember that EPSim allows you to model an embedded platform, that it enables you to co-simulate the embedded platform with your control logic, with your control algorithms, that you can evaluate the impact of the time delays on the overall behavior of the system. And as such, it enables you to do that in the early stages of your design process, so it enables you to reduce the overall design time. If you need more information or you have questions, then you can ask them in the Q&A, or if you have an interesting case study for us, then you can always contact me using the details below. Thank you very much for your attention.
So thank you, Ken, for again a very interesting presentation, also on a different topic than the previous ones. So we are coming towards the conclusion of this webinar. As far as I see, there are there is only one open questions that we didn't answer during the presentation because it was a question for the last speaker. But I propose that we will come back to the person who has asked the question bilaterally. And I would like to remind you one thing. First of all, to please fill in our evaluation form. You can do it, we will send a link, but you can also scan the QR code that you see on this slide and fill in the evaluation. That will be very much appreciated from us because any feedback is valuable to improve for our next events. We also like to remind you that there is a webinar, the third webinar from FlandersMake. It is planned next week on Tuesday, also at 11 o'clock, and deals with automation of the creation of digital work instructions. So I hope you will also join this. I hope you enjoyed the presentation and you have learned something and see maybe some possible future collaboration with FlandersMake. So again, I think this was also mentioned in the Q&A that we will provide you with the presentation in a PDF format where you can also find the contact details of the presenters. Please feel free to contact them or to contact me in case you would like to have some additional explanation about the developments done at FlandersMake and possible collaboration. So I finally hope that you enjoyed this webinar, and I will also to thank all the presenters for their time and their very interesting and clear presentation. Thank you, and hope to see you in our next webinar. Bye.